Hi everybody, welcome back to the second part. So now we want to discuss embeddedness ensuring quantities for planar curves, and we will get back to the two candidates for extending the Li-Yau result for the Willmore energy, which were defined in the first video. So the question now is, can small bending energy of a curve guarantee embeddedness? And well, as you see from the title, unfortunately the answer is no in the case of the total curvature K. So here's the theorem. If we have the total curvature energy K defined here, then the infimum of K among immersed curves is the same as the infimum among non-embedded immersed curves, and both infima are equal to 2 pi. And the infimum on the right, so among non-embedded curves, is not attained. So this means that despite its strong topological features, the total curvature K cannot detect self-intersections. Okay, so let me give you a sketch of the proof. And so actually we always have that the total curvature is larger than or equal to 2 pi. This is Fennichel's theorem, which we discussed briefly before. And what we do now is we make a construction of a curve which is non-embedded, but such that its total curvature approximates 2 pi, converges to 2 pi from above. Okay, and how we do that is we take a segment of a circle here, this yellow part, where an angular region with an opening angle beta is missing. So this is the part which is missing, and then we glue at the tangent a straight line here, and we do the same thing here, and then on the right we do the same thing symmetrically. So we also have a circular region there. The circle, we can take a circle with a radius 1, for instance. So we can assume that this has length 1. And what is clear is that now if beta goes to pi over 2, then this Pac-Man shape becomes, so the mouth opens more and more, and the self-intersection point, which was here in the first picture, it moves to the right and it converges to infinity in some sense as beta approaches pi over 2, because then the two lines want to become parallel. And this basically already indicates what happens to the energy. So what we want to compute now is we want to compute the total curvature K of gamma of this curve here. And we can split that up into two integrals. And the first one where we take this the two circular regions, and we integrate the absolute value of the curvature, which is just 1 if we take a circle of radius 1. And then we add the X-shaped part in the middle, where the curvature is 0, so it does not play a role in the integral. And well, what happens now, as beta goes to pi over 2, those two circular regions will become perfect half circles. So in particular, as beta goes to pi over 2 from below, this will converge to the integral over one whole circle with curvature 1. So this will just be equal to 2 pi. 2 pi. And this gives us basically the result, namely that the infimum among non-embedded immersed curves is equal to 2 pi. And because of the characterization of the inequality, of the equality in Fennichel's theorem, we can conclude that the infimum on the right is not attained, because any curve with total curvature 2 pi would have to be convex and embedded. Okay, so this is the first result we found, that for the total curvature, such a Li-Yau inequality type result is not possible. Fortunately, there's a positive answer for the elastic energy. So if we take an immersed curve gamma and we define its elastic energy by the L2 integral of the curvature, and if we now assume that the elastic energy multiplied with the arc length is below some critical threshold C star, then gamma is an embedding, and the threshold can be explicitly characterized. It's the energy level, so the level with respect to the energy E times L of the figure 8 elastica gamma star, which we saw in the discussion of elastica in the first video. So this means here we have this positive answer. So we have a quantity, curvature quantity, whose smallness can be used to ensure that the curve is embedded. Let me make some comments about this result. So first of all, since gamma star, the elastic figure 8, is not an embedding itself, so since it has a self-intersection, this threshold is automatically optimal. Secondly, this is now a scaling invariant quantity, so the energy E times L is scaling invariant, whereas E itself was not. And this now easily follows, because from the definition one easily gets that the energy of R gamma is 1 over R times the energy of gamma, and the length of R gamma is exactly R times the length of gamma. So those two factors of R, they cancel out now, and this makes the quantity E times L scaling invariant, which is good because the property of being embedding is also invariant with respect to rescaling. A third point is that the critical points of this energy E times L, so if you set the Fraser derivative of E times L to be 0, then you get this Euler-Lagrange equation down here, which if you compute it carefully, you see that this is just the integral form of the elastica Euler-Lagrange equation for some value of lambda. So a critical point for the energy E times L will have to be an elastica. And this is a crucial observation, because this is the way how we want to characterize the optimal threshold later. Okay, so now let's dive into the proof of theorem B. The idea will be to use a variational method to obtain a minimizer for a certain problem, and then we will have to take a closer look on the properties of this minimizer, and we want to use the classification of elastica. Okay, so what is the variational problem I want to introduce? What we want to do is we want to minimize the functional E times L on this set A on all W22 curves, closed W22 curves, which are immersed but non-embedded, right? Considered as a subset of the Sobolev space W22. And it is clear that if we can find an optimal threshold C star such that any curve with energy E times L below C star is embedded, then this value C star, if it is optimal, has to be the infimum of the energy E times L among non-embedded curves. And this is exactly what we do. We do this minimization procedure to find our critical threshold. And this is a variational problem, since the space of the domain is one-dimensional. It's not too difficult to prove existence of a minimizer here via the direct methods in the calculus of variations. So I will give a rough sketch on the existence theorem now. So here is the existence theorem. First, there exists a minimizer gamma bar of this energy E times L in the set A. So the infimum is attained. for this gamma bar. And how do we prove that? So the first step for the direct method of calculus of variations is that we take a minimizing sequence, gamma n, in the admissible set A, and now due to the invariance of the energy, we can assume that after rescaling, that the length of these curves gamma n is 1 for all n, okay, just by dividing by its length. We can furthermore translate these curves such that they all hit a fixed point, the origin in this case, and we can furthermore reparameterize them in such a way that they are all arc length parameterized. Why is that advantageous? Because with this renormalization, the energy just becomes the L2 norm of the second derivative. And what we get then is, because we have a minimizing sequence for the energy E times L, where L is now equal to 1, E is bounded, the energy of gamma n is bounded, and this means that the L2 norm of the second derivative is bounded, so gamma n is bounded in the Sobolev space W22. And now comes the advantage of the elastic energy. W22 is reflexive, so after passing to a subsequence, we may assume that gamma n converges weakly in W22 to some limit gamma bar. And then by Sobolev embedding theory, we can also assume that gamma n converges strongly in C1, the C1 topology. This implies that since gamma n is parameterized by arc length, so is the limit gamma bar. In particular, it's an immersion, and it also has length 1. Okay, so this is the second step. Now the third step is that we want to show that this is actually a minimizer. So what we do now is we compare the energy to the energy of the minimizing sequence. And actually, this is a general result. The norm in L2 is lower semi-continuous. So we have that the energy of the limit gamma bar the elastic energy can only be smaller than the energy the energy of the limit, right? But this lim_inf on the right side here converges to the infimum in the variational problem, in the minimization problem. So this means that the energy E times L evaluated at gamma bar is minimal. Well, almost. There's one tiny part we were missing so far, namely that we do not know whether the gamma bar is actually in the admissible set. So it's a gamma bar is a W22 curve. It's an immersion that we saw in step 2, but it's not clear if it's also non-embedded, so it could certainly become embedded a priori. However, this actually cannot happen, since the set of embeddings is an open subset of the C1 curves. And this, it's not super immediate, but it's relatively elementary to show. And with this, we have set the theorem about the existence here of a minimizer. In particular, this already implies that we can find some value of C star such that our theorem B holds, such that we can conclude from energy below C star that the curve is embedded. But this is in some sense not so valuable yet, because we do not know how large this constant C star is. And we do also not know which curves attain the value. And this we want to understand, so we want to understand the minimizer, the gamma bar, better. Our goal is to show that gamma bar is in fact an elastica. Okay, why is that? The reason for that is the following lemma, namely, if we minimize the energy E times L among now non-embedded elastica, then this minimum is attained for the figure 8. Yeah, for the figure 8 elastica gamma star. And for this one can explicitly compute its energy, which is something 112. Okay. What I would like to remark now is that this subset of W22 is in fact also a subset of the admissible set in the minimization problem. So a priori, the minimization, the gamma bar could have a smaller energy than the figure 8. Okay, so but we will eventually show that gamma bar is an elastica, and then it has to be the figure 8 by this lemma. Yeah, I don't want to go too much into details of the proof of this lemma, but basically it only relies on the fact that closed elastica in R2 can only be the figure 8 and a circle and multiple coverings of those. And so the non-embedded ones can only be multiple covered figure 8s or at least twicely covered circles. And then one just has to compute the energies and compare them. Okay, so what this lemma gives us is that if we can conclude that gamma bar is an elastica, then it has to be the figure 8 elastica by the minimality, and the theorem B follows from that. Yeah, here's again a plot of the elastic figure 8 to remind you that this figure 8 shape is a closed curve which has a self-intersection here at the origin. Okay, so we want to show that gamma bar is an elastica. How can we do that? Well, this would be easy to see if gamma bar was an interior point of the admissible set, right? So if gamma bar is an interior point, then we are allowed to vary in all directions phi, so we can perturb the curve in any direction phi, for any test function phi here, and then we would be able to conclude that the first variation vanishes of the functional E times L, and this implies that that gamma bar is an elastica then. Unfortunately, the problem here is that the set A is not an open set. So the set A was the non-embedded immersions, which is not an open subset in the W22 topology. And let me give you an example what can go wrong. And this is here the picture you can see. So if you have a curve where you have a self-intersection here, where in some sense the curve only touches itself tangentially, so the two tangents are anti-parallel in this point, then you can find a tiny perturbation and go up a little bit in the upper part and go down a little bit on the lower part, such that this self-intersection breaks, and you can do this for arbitrary small epsilon if you choose the phi accordingly. This means that A is not open, right? On the other hand, if the self-intersection of gamma bar is non-tangential, as it is in the picture on the right, then we have stability. So then any perturbation will still have a self-intersection. So the blue curve has a self-intersection here, and if we do the arbitrary perturbation here in green, then this still has a self-intersection here. So this non-tangential, or sometimes also called transversal self-intersections, are stable in some sense. Good. What does this mean? It means that in order to prove our main result, we want to show that gamma bar is an elastica, and we want to rule out basically this tangential self-intersections. So what we do is we carefully study this set where the curve intersects itself, the set of self-intersections, which can be seen as kind of a free boundary of this variational problem. And we will analyze the properties of this set very carefully. And here's our strategy to do that. So we denote the set of self-intersections by S. So those are the points in the image space where there are two distinct pre-images which are sent to the same point P. Okay, and what is our strategy? It consists of 3 steps. We will first show that the set of self-intersections is actually only one point. And then we will study the pre-images because, this is what we are really interested in. The pre-images of this point. And we will show that it consists precisely of 2 points. So the point P0 has multiplicity 2 under the map gamma bar. And in the third step, we will then show that the self-intersection is non-tangential. In particular, this picture A from the slide before, where the 2 curves were just separating under a small perturbation, this cannot happen for the minimizer. So we want to show that this determinant is non-zero, which just means that those 2 curves are those 2 tangent vectors are linearly independent. Okay, so let me now give you a rough sketch of the proof of the first property. So we assume that we have 2 distinct points of self-intersections, and let me draw them here. So say one is here and the other one is here. So here's the P1 and here's the P2. A priori, one of them could be a non-tangential P2 here, and the other one could be tangential as the P1 here. And what I want to show now is that the gamma bar satisfies the Euler-Lagrange equation in a neighborhood of any point in the pre-image. So let me draw the circle maybe here. That's S1, and that's the map gamma bar, so to say. And let's say the x0, which is sent to P1 here, is somewhere here. Then we want to find a neighborhood where the Euler-Lagrange equation is satisfied. And it is actually not too difficult to find such a neighborhood because, well, if we take any function phi with a compact support, so any phi smooth test function with compact support in, I don't know, say x0 minus delta with x0 to x0 plus delta, then the perturbing gamma bar with phi will not change the value here on the right hand side. Right? Here it will not change. So the phi does only have an effect in a neighborhood of P1 where it may break the self-intersection as the green arrow indicates. However, there's still one self-intersection left. That means that the perturbation gamma bar plus epsilon phi is still in the admissible set A for any phi in a neighborhood which has support in the neighborhood of x0. And because of that, in this neighborhood, the Euler-Lagrange equation has to be satisfied because we are allowed to use any phi as long as its support stays in the neighborhood of the x0. And this gives that the Euler-Lagrange equation is satisfied in the neighborhood of x0. And then so this proves this first mini step that the Euler-Lagrange equation is satisfied in pre-images of the free boundary of the set of self-intersections. To continue the proof, one can similarly show that the Euler-Lagrange equation is also satisfied in a neighborhood of any point which is not in the set of self-intersections, so which is not a point where the curve intersects itself. This you can do with a similar argument as I tried to sketch on the previous slide. And from then, well, the Euler-Lagrange equation will have to be satisfied globally, right? you can see that by so it's satisfied in the neighborhood of every point which is not in the pre-image of S, and it's also satisfied by the previous slide for every point which is in the pre-image of S under gamma bar. So it's by a partition of unity argument, you can then show that the Lagrange equation is satisfied globally, and hence the gamma bar is an elastica. Then, by minimality, it has to be the figure 8 elastica. But the figure 8 elastica does only have one single point of self-intersection, right? It's the 8 shape which only intersects at the origin, right? Here. Well, this contradicts our assumption that the set of self-intersection consists of more than one point. And actually, the same strategy works for proving 2, namely that the single self-intersection we have has exactly multiplicity 2. So I will now, since we have proven 1 and 2, I will now try to sketch the proof of 3. So now we know that the pre-image of the self-intersection consists of 2 points, and we want to show that at these points the tangents are linearly independent. To that end, we will use a small tool from the theory of planar curves, namely the following lemma. If we have a curve in A in the admissible set, so a curve with a self-intersection which has winding number, so the winding number is defined here. It's the integral over the curvature without absolute value, so it's just the sign curvature inside here. And if this winding number is not plus or minus 1, then the gamma is an interior point of A. So in particular, well, if we are an interior point, then we know that we can use the classification of elastica. Okay. I don't want to speak about the proof of this lemma, but we will use it now in order to prove the result 3, namely that the two tangent vectors at x1 and x2 are linearly independent. So we now assume that they are equal. So if they are linearly dependent, then if we normalize them to have length 1, like we do with taking the ds, then they are either parallel or equal, or they are anti-parallel, so that one is the negative of the other. And in the case that they coincide, then we can then the curve looks like so. And what we can do now, so the curve looks like so means I start here from this H shape and then I go around like this, right? So at this point here, I go through it twice, but the two tangents are the same at this point where I intersect. And if we now split it up into two curves, they are both closed curves, and they are embedded because we know, or we have already proven, that S consists only of a single point. So there's only one self-intersection. And well, if we now split it up into two curves, like so gamma bar restricted to x1, x2, and gamma bar restricted to x2, x1, then those two curves are embedded closed planar curves. And there's a version of the Gauss-Bonnet theorem in one dimension if you want, or it's also called Hopf's Umlaufsatz, which says that the embedded closed curve, so any embedded closed curve has winding number plus or minus 1. So this means that this here is plus or minus 1, and this here is also plus or minus 1. Well, but then the sum can only be minus 2, 0, or 1, or 2. So in particular, the sum is always not equal to plus or minus 1. And this means, by the lemma, that gamma bar is an interior point of the admissible set A, and hence, by the analysis before, it has to be an elastica, and by minimality, it then has to be the figure 8. But it cannot be the figure 8 because the figure 8 looks like so and has a non-tangential self-intersection, right? But we assumed that it has a tangential self-intersection. So yeah, here's the things, the summary of the argument again. So if it was if gamma bar is an interior point, it has to be the figure 8. So it cannot have a tangential self-intersection, but we assume that it did, so there's a contradiction. And a similar contradiction you can deduce if you assume that the two tangents are anti-parallel and have opposite signs. Yeah, but I don't want to discuss this in detail. Okay, so this is almost it for the proof of theorem B. Now we can put everything together. So now we know that the minimizer gamma bar can only have one single self-intersection, and this self-intersection must be non-tangential, right? Okay, because everything else will lead to a contradiction, basically. Okay, well, what we do now is if we take an arbitrary test function phi and we perturb gamma bar by phi, then because the intersection is non-tangential, it's stable, right? So gamma bar plus epsilon phi will still have a self-intersection. This is the picture from before again. The self-intersection was here and the perturbed one is here. So it still possesses a self-intersection, so it's still in the admissible set, and well, then we can deduce that gamma bar is a critical point. So gamma bar is an elastica, and by minimality it thus has to be the figure 8. And to sum things up, we have proven by our minimalization process that any non-embedded immersion has the elastic energy multiplied with length bounded from below by the corresponding one for the elastic figure 8. This means, on the other hand, that if a curve, an immersed curve, lies below this threshold here, this C star, then it has to be embedded. And this proves the result in theorem B. Okay, so thus we have seen that it is possible to describe, to guarantee the embeddedness of a curve in the plane purely in terms of its energy, in terms of its elastic energy and the length. And what I want to do now is I want to discuss the effects this has for the corresponding geometric evolution equations. So let's talk about the elastic flow. And I want to focus on the length-preserving elastic flow now. So we say that a family of smooth curves defined on this time interval 0t cross S1 is a length-preserving elastic flow if it satisfies this geometric evolution equation here. Here we use the notation nabla S for the normal projection of the arc length derivative ds. So this is just a symbol if you want. And this is now really describes a PDE, a one-dimensional PDE in space and time. And the Lagrange multiplier is given as a quotient of these two integrals. Note that the denominator is always non-zero because the elastic energy is bounded from below for closed curves. So this is the length-preserving elastic flow, and to justify the name, one observes by a direct computation that the length is indeed preserved. So yeah, you can check that by computing the variation of the length, which is given by testing the evolution equation against kappa, and then you find that lambda is chosen exactly in such a way that this is 0. Okay, so the length remains preserved. I should mention that there is also another version of the elastic flow where instead of lambda given by this integral terms and depending on the solution itself, one considers a fixed positive scalar lambda, and then the length is not fixed but rather penalized by the flow. Okay, and this flow has been analyzed in any codimension, in any RD. In particular, by the work of Jukuvat and Schätzle, we know that it exists for all times, and as t goes to infinity, it subconverges to an elastica. For the case of planar curves, this also follows from the work of Polden, and there's also a second order version of this flow by Wen. Okay, so how can we make use of our main result now? Well, let me first say that this equation, despite that it's a one-dimensional PDE, it's still not. It's still a geometric evolution equation. It's a fourth order. It's also non-local due to the integral nature of lambda and quasi-linear, of course. But in particular, because it is fourth order, the maximum principle does not apply. And this is what we would usually use if you want to speak about conservation of embeddedness. Well, luckily, we can prove that embeddedness is preserved even for this fourth order flow by our threshold for embeddedness. And why is that? Well, this is an elastic flow, and the reason it's called elastic flow is because it decreases the elastic energy, and since it also fixes the length, the Willmore energy we discussed, so the product of the elastic energy and the length, decreases as time evolves. So we get the following consequence of our theorem B. If we start this length-preserving elastic flow with a curve with energy below the threshold of the figure 8, then the flow will be embedded for all times. So the initial datum will be embedded and the curve will not intersect itself, never. And this follows from our inequality and the energy decay, which is written above the theorem. Moreover, we can also show that it not only subconverges, but it converges, and we can even classify the limit, which is then a circle with the given radius. So the convergence, maybe one word about that. So the convergence here, since we already have subconvergence by the work of Jukuvat-Schätzle, this follows from a Wojciechowicz-Simon inequality argument. Okay, then I would like to thank you for your attention. Thanks for listening. If you have any questions or want more details, you can check out the preprint on the archive, or you could also come to the Q&A session for the Geometric Analysis Festival.